All right, so we're going to be solving problems with exponential and logarithmic functions. All right, and I'm going to take a look at, like I said, a lot of different science aspects. They're all true. And the first one is dealing with the Richter scale. So we have example one. 3 earthquakes occurred in locations A, B, and C with magnitudes 4, 6, and 7, respectively, on the Richter scale. All right, so A says, how many times stronger was the earthquake at B than the earthquake at A? All right, so we're going to compare earthquake A and B. Now, A is a 4 and B is a 6. Now, the Richter scale goes up by ones. All right, so when I'm comparing a 4 to a 6, I'm going to write 4, 5, and 6. Now, how the Richter scale actually works is that when you have an earthquake that is a 5 and I compare it to a 4, because it's on a logarithmic scale, it's not one bigger. It's in fact 10 times stronger. And then if I compared a 6 to a 5, a 6 is 10 times bigger than a 5. Because again, every time you go up one number on the Richter scale, you're going up by a multiple of 10. And so in this case, if I'm comparing a 6 to a 4, 10 times 10 is 10 squared, which equals 100. And so, in fact, a 6 is 100 times stronger than a 4. It's often why you'll see a 4 is just little tremors, where 6 is buildings shaking. And it's because, again, it's on a logarithmic scale. Now, if I get to B, where it says how many times stronger was the earthquake at C than at earthquake A? So C is a 7. A is still a 4. So again, because the logarithmic scale goes up by ones, I'm going to write 4, 5, 6, and 7. And again, every time we jump up a number on the Richter scale, we're going up by a factor of 10. And so when I compare a 7 to a 6, it's 10 times stronger. And so when I compare a 7 to a 4, it's 10 times 10 times 10 times stronger, which if I multiply 10 by itself 3 times would be 10 cubed. And so in fact, a 7 is 1,000 times stronger than a 4. And a 7 is when you get some major damage going on. Now that's working with the Richter scale when it's nice numbers. What I mean by that, no decimals. But in example 2, if one earthquake, a little more realistic here, has a magnitude of 3.5 on the Richter scale, and a second earthquake has a magnitude of 6.2, compare the intensities of the two earthquakes. Now, to compare these two earthquakes, I'm going to take, to compare here, I'm going to take this 6.2, and I'm going to kind of divide it by my 3.5. The difference here, though, is that the Richter scale, again, goes up by a factor of 10. And so I'm going to take 10 to the power of 6.2 and divide it by 10 to the power of 3.5. And again, with our theme today, I have a lot of exponent rules here. When you have power divided by a power and they have the same base, we keep the base the same. And we subtract the exponents. So I get 6.2 subtract 3.5. And if I do those, I get 10 to the power of 2.7, which is, let me see here, 10 to the power of 2.7. I get 501.19. So in the end, that means that a 6, oops, shrink up my words, a 6.2 is 501.19 times stronger than a 3.5. So again, there's a way to do the easy ones, which again, no decimals. But when you do have decimals, we have to do a little bit differently. Even though you can do the easy ones the same way. It's just a little bit shorter doing it this way when you're just doing how many steps up you're taking. Now, another scale that is a logarithmic scale is the decibel scale. And that's something we've done a few questions on. So according to the table given out in class, I haven't given that out, but amplified, you got to take my word for it here. Amplified rock music has a loudness of 120 decibels. And an ordinary conversation has a loudness of 50 decibels. And whispering has a loudness of 20 decibels. A, how many times louder is an ordinary conversation than whispering? All right. So again, we're comparing a ordinary conversation, 50 decibels, with 20 decibels. Now here is, they're both logarithmic scales in terms of the Richter scale and the decibel scale, but here's the difference between the two, is that the decibel scale does not go up by ones. In fact, it goes up by tens. All right, so if I'm comparing a 20 to a 50, I'm going to go 20, 30, 40, and 50. But just like the Richter scale, every time you go up 10 on the Richter or on the decibel scale, you are going up by a factor of 10. And so from going from a 50 to a 20, I would be multiplying by 10 each step. And so if I'm combining those 10 times 10 times 10, which is again 10 to the power of 3, a 50 decibel scale would be 1,000 times louder. All right, now if I'm get to B, where I'm comparing a rock concert, 120, to a 50, again, I can do a similar way, and then I have 50, 60, because again, the decibel scale goes up by tens, 70, 80, 90, 100, 110, 120. Okay, so in this case, a 60 is 10 times bigger than a 50. See how many jumps we have here. Then we go to an 80, again, multiplying by 10, going to 90, multiplying by 10. Keep doing the factors here. Let's see here. Woo. Lots of multiplying by 10. And so 10 to the power of how many tens do I multiplying by tens here? 1, 2, 3, 4, 5, 6, 7. I would multiply 10 by itself 7 times, which is, yikes, big number. 10 to the power of 7. Oh, it's going to be 1 with 6 zeros, 7 zeros. 10 million. So when I'm comparing a rock concert to an ordinary conversation, a rock concert is 10 million times louder than an ordinary conversation. And again, a little FYI for you, I believe the highest the decibel scale goes up to is about 140. After that, eardrums pop. Not pleasant, so I've heard. Let's see here, example 4. So again, we can have a situation where we don't get those nice numbers. So in this case, the sound level of a person screaming is 104 decibels. The noise level of the same person shouting, this person's got issues, is 87 decibels. How many times louder is the scream over the shouting of this person? All right, so we're comparing their scream to their shouting. So again, just like I did before with the Richter scale, I am going to compare these two by dividing 104 divided by, there's going to be a catch here though, 87. But again, as we go up the ladder on the decibel scale, it's by a factor of 10. So my base is 10. Now, here is the catch with this one, with the decibel scale, is that the Richter scale goes up by ones, but the decibel scale goes up by tens. So this 104, I'm going to divide by 10. This 87, I'm going to divide by 10. So this 10, the big 10, the base, is because each time we go up the Richter or the decibel scale, it's by a factor of 10. This 10 in the denominator is because the decibel scale actually goes up by tens. All right, so now I have 10 to the power of 10.4. And in the bottom here, I have 10 to the power of 8.7. And again, I have a power divided by a power with the same base, so I keep the base the same. Subtract my exponent, so 10.4 minus 8.7, I end up with a 1.7. And if I take 10 to the power of 1.7, I end up with 50.12. And so this person's scream is 50.12 times louder than their shouting. All right. What else we got here? Again, more science stuff coming on here. For all of you in chemistry. In chemistry, the pH level, which was, in case you don't know, I'm not asking you to know, but just so you do, the measure of the acidity or alkalinity of a substance is based on also a logarithmic scale. Using the formula, your pH is equal to negative log of H plus, where H plus is the concentration of hydrogen ions in moles per liter. I don't necessarily know what all that means, or if I do, I can't explain it. But that's just some chemistry stuff for you, for those, again, you chemistry buffs. A says, find the pH level of a substance if hydrogen concentration is 0. all that moles per liter. So it says, find the pH level. We're looking for our pH level. All right, so our pH level is equal to negative the log of H plus, which in this case is 0.000, make sure I count the right amount of zeros here, 001. All right. Now I can just flat out figure that out. So I take the log of that very, very small number. And in fact, because it's so small, it's -6. And when I have a negative sign times a negative sign, well, it looks like our pH level would be 6. All right, now here's where we're looking at for B. Find the hydrogen concentration level of a substance that has a pH level of 9.3. So now we have the pH level. So now if I substitute that into my equation, I have 9.3 is equal to negative log of this H plus. All right. So I want to solve this equation. All right. Now, the first thing I'm going to do is divide both sides by -1, because that's what this is here. That's a negative sign in front. And all that's going to do is turn that 9.3 into a -9.3. But again, what I want here is a number equaling my log function. Because as I did even in the homework take up, now I can, this plus sign is just, I guess is just to positive hydrogen here. Now I can convert it to exponential form. And again, when you just have log, there's secretly a base 10 there. And so what I have here is, there's my base of 10. The exponent is -9.3. And it's going to be equal to my answer, which is the concentration of hydrogen ions, right? Ions, yeah. And if I take 10 to the power of -3, yikes, I get, 0. Let me count them here. 1, 2, 3, 1, 2, 3, 1, 2, 3, and then a 5. And that is going to equal my amount of hydrogen ions in moles per liter. There we go. Again, just getting log equaling a number so that I can switch it to exponential form. All right. Do I have any more? Yeah, one more here. Okay. Example 6. Okay, so more science, and there's lots going on here. And this is, again, these are all true formulas. These aren't made up. The amount of water vapor in the air is a function of temperature given by the equation. Hence why you should drink a lot of water in the winter because, well, there's less water vapor and you get dry lips in the winter because it's colder and there's less water in the air. So there's our formula, where S is the saturation of the air in milliliters per cubic meter, and T is the temperature in degrees Celsius. Find the temperature of the air if the saturation is 50 milliliters per cubic meter. So this here is our saturation, which is our S value. So in our formula, I have 50 is equal to, let's see here, I've got 5.06 times 1.07 to the power of 0.95 T. All right, so I got to solve for an exponent, which means at some point here I'm going to take the log of both sides. Not yet, though. I'm going to get rid of this 5.06 that's attached. So the only way to get rid of it is to divide both sides by that 5.06. And what I do to one side, I got to do the other here. And so let's see here. 50 divided by 5.06, got to be 9 something, I'm thinking. Yeah, 9.88 is equal to, now I just have this, I might as well put it in brackets, 1.07 to the power of 0.95 T. All right, so now my next step here is to take the log of both sides. It's the only way it's going to happen. All right, so I take the log of 9.88. Now I'm going to take the log of the right-hand side, and I'm doing that again because I'm going to use that log rule where I'm bringing the exponent down in front. All right, so that exponent was on the 1.07. Because I took the log of both sides, I can use that log rule to bring it back down. All right, so now I'm going to find the log of 9.88, and it's 0.995, and that's equal to, let me see, I got 0.95 T times the log of 1.07. That can't be a very big number. And it isn't. It's 0.03. Okay. Further simplifying, we got these three things multiplied on the right-hand side of our equation. Doesn't matter which order you multiply. So I'm going to take that 0.95 and I'm going to multiply it by 0.03. And I get 0.028 times my T. And then, of course, my last step here is to get T by itself. So I'm going to divide both sides by that 0.028. And those T's divide, or those 0.028s divide each other out. And so our T value is whatever our 0.995 divided by 0.028 is. And so if our saturation level here is 50 milliliters per cubic meter, I end up with a temperature of 35.5 degrees Celsius. That would be the saturation of the moisture level in the air. Would be 50 milliliters per cubic meter if the temperature is 35.5 degrees. Now we get to B. Basically the same thing here, but it says find the temperature of the air if the air saturation is 5 milliliters per cubic meter. And so again, I have my S value. So I'm going to plug in a 5. That's going to equal, again, my formula here was 5.06 times that 1.07. And our exponent here was, again, the 0.95 times t. All right, I'm going to follow the same steps I did up here. So again, the first thing I'm going to do is divide by this 5.06 on both sides. And I'm solving for an exponent, so I am going to have to use that log rule again. So these 5.06 divide each other out. 5 divided by 5.06, it's going to be a decimal. Oh, yeah, it's just 0.99 equals 1 point. I'll put it in brackets. Why not? 1.07 to the power, again, of that exponent, which is 0.95 t. All right, so again, solving for an exponent. This is something we've done. We're going to do it again later today or in our next lesson as well. But I'm going to take the log of both sides. And again, I'm doing that so that when I take the log of my right-hand side here, I can move my exponent down in front, which is the 0.95t. And again, now it's going to be multiplying log of 1.07. All right, so now it's just taking the logs, getting rid of that. So take the log of 0.99. I end up with, again, small number, so I get a negative 0.004 equal to 0.95 times t times, what's the log of 1.0? Sorry, I already had that. That's 0.03. All right, once again, didn't I do that? Well, let's just stick with what we got here. So I'm going to multiply now my 0.95 times my 0.03. And we end up with that 0.028 times t. All right, and now the final step. Let's get t by itself here. So I'm going to have to divide both sides by 0.028. So I'll do that over here too. And so my temperature is going to be whatever negative 0.004 divided by 0.0028 is. And my t is equal to negative 0.16 degrees Celsius. So almost 0 degrees. So, you know, a little FYI here for you. There's not a lot of moisture in the air, or the air doesn't hold a lot of moisture when it's cold. When it's warm, it gets humid. It holds a lot of moisture. Hence why your clothes dryer pumps warm air and not cold air. Warm air is because that warm air sucks water up into the air, and that's what dries your clothes. And that's why you won't have much luck. I can after, yes, it'll be right now. So there we go.